Summary of what we should know about rational functions. Rational function is a function where you have a polynomial divided by a polynomial. We use r of x to indicate in function notation a typical rational function. The rational function has zeros where the numerator is 0 and the denominator isn't 0. So it crosses the x-axis at those values of x. It has vertical asymptotes when the denominator is 0 and the numerator isn't. And the y-intercept is at 0, r of 0. Also, when the absolute value of x is large, that means x is a large positive number or a large negative number, it behaves like a vertically stretched y equals x to the p, like some multiple of x to the p, where p, the power of this function, is the degree of the numerator minus the degree of the denominator. Okay, so for example, we have this function. Now, numerator is 0. When x equals -3. That's the only way the numerator can be 0. And of course that's what makes this term 0, because this term can't equal 0, at least not for real numbers. We're talking about real valued zeros here. Okay, it's a quadratic. You can check the discriminant and you find that it can't be equal to 0. So we have where x equals 3, this thing goes through 0. Okay, denominator is 0. When x equals 1. So we have a vertical asymptote. And we've talked about why we have a vertical asymptote. Now we're just summarizing it. Here's the line, x equals 1, this dotted line, and the graph has to be asymptotic to this. Okay, the y-intercept is at 0, r of 0. In other words, to get the y-coordinate of this intercept, we plug 0 into the function, and we get what? 3 times 2 over -1. That's -6. So let's put -6 down here. Let's see how we're going to do this. Okay, I'm going to put -6. Well, I'm going to put the label here. It indicates this value. Well, now, the function behaves like what when the absolute value of x is large? Well, the degree of the numerator, if you multiply all this out, you're going to have a leading term of x cubed. The degree of the denominator is 1. So the degree of the numerator is 3. The degree of the denominator is 1. You subtract the degree of the denominator from the degree of the numerator, you get 2. So this is going to act like x squared for large x. That could be actually like x to the p, or like a negative x to the p, or some multiple thereof. Okay, but that's what we have. In this case, it's going to be a positive x squared because all the x terms are positive here. All the leading terms are positive, have positive coefficients. Okay. So overall, the thing is going to do like this. It's going to be a parabola. If you get out there and out there, it's going to be up here. It's going to be up here. In this vicinity, it could do something quite a bit different. So it could come down like so. Got to go through the x-axis here. Then it's got to go through the y-axis here. Then it's got to turn and approach this x equals 1 line as an asymptote. On the other side, well, it's got to be positive over here. It can't go through the x-axis because there are no zeros over here. If it went through the x-axis, you'd have to have something in the numerator that made it 0 at that point, and that's not going to happen. The only place the numerator can be 0 is when x equals -3. Didn't put the negative on that. Okay, so it's got to go up like this, approaching that parabola, and it's got to have a vertical asymptote here. The only way it can do that, it can't come up from down here because it would have to go through the x-axis. It has to come down from here, and at some point has to turn around and head back up. So that's roughly what the graph of this function should look like. Now we can't tell how high or how low this is. We can't tell at what x coordinate it actually levels off before moving back upward. So this is just not even a guess, it's just what it could look like. But this low point might be out here, it might be closer here. Okay, actually you can tell more, but you need calculus, so we don't worry about that. Okay, well, there's a reasonable graph of this function. Now let's do another example. Let's do x minus 2 over x squared plus 5x minus 6 times x plus let's go x plus 3. Okay? Well, the numerator is 0 when x equals 2. Which makes the whole thing 0 when x equals 2. Now you do have to check and make sure that 2 is not a 0 of the denominator. You plug 2 into the denominator, or you can find the zeros of the denominator and see. Okay, well, so x squared plus 5x minus 6 is a quadratic, but it can be 0 because this factors into x plus 6 times x minus 1. But we can write this in factored form as x minus 2 over x minus 6 times x plus 1 times x plus 3. And now we see that we're going to have zeros of the denominator at x equals 6. We'll put that here. The scale isn't very good, but we'll do that. At -1 and at -3. Now none of those matches the 0 of the numerator, so we don't have a removable singularity. There's no asymptote here. Okay. So there's what our graph looks like. Now, the y-intercept we get by plugging in x equals 0. We're going to get -2 here divided by -6 times 3. It's going to give us 1/9. So we have a very low y-intercept, and it is positive. So the y-intercept is at 0, 1/9, very close to 0. The overall behavior, in other words, for large x, like x to the -2, which is 1 over x squared. That's your basic reciprocal square function, that means it's got an asymptote at the origin, and it comes down like this, comes down like this. So that overall, it's going to do something like this. And over here, going to do something similar, approaching the x-axis as an asymptote. You can also reason this out from the fact that if x is really big, the denominator is a whole lot bigger than the numerator. We've talked about that. I like the idea that it acts like 1 over x squared if you get away from the origin. Okay, so, well, what's that mean? You've got an asymptote at -3, and it's got this behavior. It means it comes down from this asymptote and approaches the x-axis rapidly as an asymptote. I've got it a little bit too high there, but that's okay. Can also happen. Okay, over here, it's going to do the same from this asymptote. It's going to come down here, and it's going to approach positive x-axis as an asymptote. It's going to have an asymptote here. Okay, now it's got a 0 at x equals 2, and it's positive if pretty small. Here, what's that going to do? Trying to look at how to draw it and figure out how to explain it, why it does what it does, because what it does is it comes down from here, passes through this point, goes over kind of close to the x-axis, and then through here and back down. Between here and here, it can't become 0. You can actually check the sign of the thing. At x equals -2, you would have a negative up here, you would have a negative here, and you'd have a positive here, so it would be positive. That can't be. Something's wrong. Got to change sign there. Got to change sign there. Can't have a 0. So actually, I've got a little bit of a contradiction going on here. Something isn't right in my thinking. I'm using some things that I was teaching the course, but I want to leave that for your regular course, which is the fact that the function can only change sign at an asymptote, and I don't know what I was thinking. Okay? So I just explained it to myself. It has to do this here. It has to be negative between -3 and -1 because it can't change sign here between these two numbers, because it can't go through 0. It has to go through 0 to change sign, or it has to cross an asymptote. Okay? And if x is -2, we're still getting a negative over a negative, which is positive. Which can't be. I'm going to leave it as it is. It has to look like this, but when I check the sign here, it doesn't work. So I'm going to put a big question mark here. We're not going to worry about it. You can worry about it in your course. And actually, if I look at it here, it's got 3 negatives in here, so it is negative. Yeah, okay. So you kind of overlook that, but there's what the graph looks like. Now what you've seen is simply how the zeros of the numerator determine the zeros of the function, The zeros of the denominator determine the vertical asymptotes. And the difference between the degree of the numerator and degree of the denominator determines the function it looks like if you step back and look at it on a really big scale. So this one looked like the squaring function, so it kind of comes down here, but then things happen in here, but then you get out here and it starts acting like the squaring function again. Okay, this acts like the reciprocal square function, but when you get in close, these zeros and asymptotes make things, well, distort the graph of the overall function. Okay, so there it is.